Welcome everybody to this AJS. Today with us we have Matteo Zancanaro. Matteo is a last year PhD student and he works with Professor Gianluigi Rozza and Dr. Giovanni Stabile, and today he will talk about closure models for reduced order methods, compressible flows approaches, a balance between consolidation and innovation. Thank you, Matteo.
So thank you, Maria, for the introduction. So as Maria already said, today I'm gonna talk to you about closure models for compressible fluid dynamic reduced order methods. And this is a work in collaboration with Dr. Giovanni Stabile and Professor Gianluigi Rozza. So this is a brief overview on the physical applications we are interested on. So basically, turbulent compressible flows are actually there in many different fields and also at many different scales. So as you can notice from the slide, you use this kind of representation for example, different types of engineering or for nautical problems or environmental ambits. And in fact, if you take a look to the pictures, for example, the top right one is a picture of Jupiter. And of course, this is a macro scale, but still you can notice that there's a lot of turbulence, and it's pretty nice to be able to see it like that. And actually, there are also something that is to me really interesting. There are the same convective cells that you may find in any weather representation also for Earth. So, but this is another story. I mean, it's just an interesting to be noticed. So before moving to the objectives, I just would like to underline a few points. So let's say that the fluid dynamics simulations keeps on be very important in many different fields, since we would like to be able to predict different aspects of the behavior, of the fluid. And one point that has to be underlined is that for a lot of those applications, these problems are affected by the presence of turbulence. So you have to somehow try to manage this thing. And since in this work we're gonna talk about parametric PDEs, it happens that usually you are requested to solve the same equations for many different parameter values. So of course the computational cost can become unfeasible. So for this reason, we would like to develop a reduced order method that should be as efficient as possible, but still it should retain a high level of accuracy. And it should be as general as possible, so that it is very versatile and you can apply it to different conditions. And also it should be reliable for different kinds of parameterization. For example, in this talk, I'm going to show you some results about both physical and geometrical parameterizations. So this talk is going to be divided into 4 main parts. At the beginning, I would like to briefly give you an introduction about compressible Navier-Stokes equations. Then just would like to mention turbulence modeling and how it works. Then I'm going to give you a non-detailed presentation of the resolution techniques in the sense that in case I had to give you a detailed presentation, it will be really too long and maybe too boring. And at the end, I'm just going to show you the results that we obtained for 2 different applications, as I already said. So here we are. These are the compressible Navier-Stokes equations in their full and continuum formulation. So the main equations are basically 3. There's the continuum equation, the energy equation, and the momentum equation. So here, of course, the system has to be completed by boundary conditions, initial conditions, and an equation of state that depends on the type of fluid you are working with. So here we are using this tau of u that is actually the viscous stress tensor. And I just put it here because in this tensor we are just to underline that here we are using a Stokes hypothesis for Newtonian fluids. So this is not a formulation that works for every kind of fluids, but just for Newtonian ones. So because of turbulence, of course, into the domain of interest, you have a lot of fluctuations for all the possible variables. But since we are just interested on macro effects, then the fluctuations, are not relevant for our studies. So the idea is to just take somehow an average of the equations and also of the variables, so that the fluctuations are no more there. But it is not that easy as it could be for an incompressible case, since you here also have the fluctuations of the density of the fluid. So for this reason, the Reynolds averaging that is commonly used for incompressible fluids here is not, useful. And that's why we are using instead Favre decomposition and averaging. So these are basically the averaging rules that we are using for the equations. In fact, if you see here, the tilde variables are the Favre averaged ones, and inside there is the averaging of the density. So after having used the Favre averaging, we can obtain these Fans equations that are pretty similar to the previous ones. The only point is that, of course, all the possible variables here are averaged. But if you notice, still there are some terms that contain the fluctuations mainly for velocity. And you have somehow to solve these problems since you're not, as I told you, interested on them. So a very common way to get rid of these terms is to use the Boussinesq hypothesis. So basically what you are saying is that the term that is here in the momentum equation, that is the Reynolds stress tensor, can be approximated as just by the use of just a linear dependence on the viscous stress tensor tau, plus a term that is depending on K, that is actually the turbulent kinetic energy. So once you did that, you still have two more terms to be modeled, and they are modeled as you can see here at the bottom of the slide. So again, they are you just try to write down everything by exploiting the dependencies on averaged quantities. So if you put all those model terms into the equations and you just pick the steady state system, since in today's talk I'm not gonna show you any kind of time dependent problem. You get these equations that are basically the Fans equations, but I mean, still there is a term here that is the mu t, that is called the eddy viscosity, that is basically a viscosity that has to be added to the shear viscosity, because of the fact that if you do not put that into the equations, since we are not able to solve very tiny scales that are in the Kolmogorov energy cascade, the dissipative scales, then of course the kinetic energy present into the system will not be dissipated in the right way, and there will be of course an amount of energy into the system that is higher than expected, and of course everything will be messed up. So moreover, we got rid of the term related to the turbulent kinetic energy, because of the fact that we are supposing turbulence to be isotropically distributed into the domain. So the divergence of that term is very small and it is not relevant for us. So of course, still you have to find out a way to express that eddy viscosity in some sense. So the eddy viscosity can be modeled in many different ways, but they all can be mainly divided into three main groups. They are the zero equation, the one equation, and the two equation approaches. So usually the two equations approaches are the most used ones. And in particular, we are using a K omega turbulence model that is a two equation model. So it works like that. You have you can write down these two transport equations for both K and omega, where K again is the turbulent kinetic energy, while omega represents the specific turbulence dissipation rate. And once you solve those equations, you just have to exploit this relation between the eddy viscosity and those two variables, and you are mainly done, let's say. So in this work, basically we want to find out a way to solve it, to solve those equations in an efficient way. So it is, we can divide, let's say, this process into three main steps. The first one regards the offline phase. So it is a phase in which you try to get as much information as possible from some full order solutions that you, of course, have to calculate before. so that you can use those equations to solve in a more efficient way the equations for some other values of the parameter. So since we want our model to be as general as possible, we don't want to be dependent, let's say, on the turbulence model that we have chosen. And for this reason, we decided to just use a classical way for what concerns the main equations, so the continuity, momentum, and energy equations, in the sense that we are projecting those equations into a reduced space so that their dimension is much smaller, and of course, it becomes more efficient to be solved. Instead, we use a neural network to approximate the eddy viscosity field, so that it doesn't really matter which was the turbulence model that has been applied during the offline phase. You just need the solutions, and you can, go on and get the online solutions. So basically, the two first steps, so the offline phase and the neural network training, are the most costly one. But once you got them, you are able to solve in an efficient way the online part. So for the offline phase, we use to find out those solutions an iterative segregated approach, in the sense that the Fans equations are not solved as they are, as a system, but they are just split up and solved one by one in a cascade way, and then in an iterative way till convergence. But since we want the online procedure to be as coherent as possible with respect to the offline one, of course, we also need some information about the path that the full order solver is taking to reach the converged solution. So for this reason, we are not just collecting the converged fields, but we are also picking up some intermediate snapshots, so that we get, as I told you, some information about how to reach the final solution. So we have to construct those solution sets, let's say, for all the possible variables, so u, p, e, and mu t. And during the online phase, we would like to be able to reconstruct our solutions as just a linear combinations of some basis functions that are just dependent on the position x, and on they have to be multiplied by some coefficients that are instead only dependent on the parameter. So now the point is, how can I get those basis functions? So if the idea is that you want to minimize the error, so the distance between the solution, the online solutions SI ROM and the offline solutions SI, it is well known that the basis functions you are looking for are the ones that you can get by the use of a proper orthogonal decomposition. That is a method in which you have to construct a correlation matrix that is here represented as capital C, that is just S transpose MS, where M is the mass matrix, that is basically the matrix containing the volumes of all the different cells of your grids. And the basis functions we are looking for are just a combination of the eigenvectors coming from these, the eigenvalue problem that you can construct on C and the snapshots that you already got. So since, as I showed you before in the equations, the eddy viscosity is just dependent on the velocity and of course on the parameter, then you can somehow think that also the reduced coefficients of the eddy viscosity are just dependent on the velocity and on the parameter. But since the velocity is just dependent on, of course, the reduced coefficients of the velocity, then you can easily say that the reduced coefficients for the eddy viscosity are just dependent on A and mu, where A are the coefficients for the velocity. So this is the neural network that we are actually using. It is a very simple one. It is a fully connected neural network. So you have all your parameters, mu as an input, and together with the online coefficients for velocity, so A, and you get the M coefficients, so the online coefficients for the eddy viscosity at the output. And this is, I mean, a very simple scheme for a neural network, and it is also not so deep in the sense that it's just containing two hidden layers where hyperbolic tangent functions, activation functions are present. So you have, of course, to train somehow that network, and so how do we do that? Basically, you first of all have to obtain the snapshot sets as mu for the eddy viscosity and SU for velocity. Then you can apply a POD to both those sets so that you obtain the basis functions, so eta and xi. Then you have to project all those snapshots over your basis functions so that you end up with their coefficients m for the eddy viscosity and a for the velocity. So here starts, let's say, the training part, the real training part, in the sense that you put into your neural network the parameters that are here represented as P and the coefficients for velocity A. Then the neural network is going to predict a new online vector of coefficients for the eddy viscosity, so M prime. And you can compare, let's say, M prime and M into a loss function so that it is telling you how well your neural network is predicting what you really want. So this loss function is just, I mean, feeding in a backward way the neural network. So you have to keep on doing this process many times. In our work, we just fixed 20,000 epochs for the training, and I mean after a certain time, you hope your neural network to do what you want. So this is a very boring slide, but I mean, it is containing the whole online phase that is the most important part for our work. So the online algorithm is working in this way. You just have to provide a first attempt coefficients for velocity, pressure, and energy, and of course the basis functions that I showed you before. Then you can reconstruct at this point the fields U star, P star, and E star. You can evaluate the eddy viscosity by the use of the neural network that you just trained. Then you can assemble, project, and solve the momentum equation so that you end up with a new U star star. You do the same for the energy equation so that you end up with E star star. And at this point, you have to exploit the state relation between, let's say, the thermophysical variables, so that you can evaluate the density rho star star and temperature T star star. And at the end, you just assemble, project, and solve the pressure equation, so that you finally got also your P star star. So at this point, you have just to check the convergence. So if the convergence has been reached, then I mean, you just have to stop. Otherwise, you go back to point 1 and keep on iterating till you obtain, I mean, a good solution. So this is a scheme resuming more or less all what I told you till now, because I mean, I can understand that it can be not that easy to be catched. So, and here maybe it is kind of more clear. So on top you have the offline part. So on top left part, you have the offline algorithm that is composed by momentum, energy, and pressure, key omega, and state equations that are somehow influencing each other till convergence. So from this algorithm, you get your snapshot sets that are SU, SE, SP, and S mu. You apply a POD to them, and you get your basis functions. So all those basis functions are used in the online phase to project the equations. And also you use the viscosity snapshots and basis functions to train your network, so that during the online phase, you don't have the key omega process anymore. You just have to evaluate the neural network that you have trained. So these are the test cases that we used to check basically our procedure. So the first one is the resolution of the flow around an airfoil, an ACA 0012, where the shear viscosity has been parameterized, so it can vary between 10 to the minus 5 and 10 to the minus 2. So the inlet velocity is equal to 250 meters per second, as you may see here from the gas constant. We are supposing to work with perfect gases, and we also suppose to be using just I mean, here we have the molar mass of the gas, and I mean all these coefficients that are just dependent on the state that you are working at. So by the use of all these data, it is easy to evaluate the Mach number that we are working at, and it is kind of 0.73. That is pretty high in the sense that you are close to the speed of sound, and for this reason, of course, you need to use the compressible Navier-Stokes equations, and you also can evaluate the Reynolds number that is kind of 10. It is I mean between 10 to the power 4 and 10 to the power 7. Of course, this is varying because we are varying the viscosity. So also the Reynolds number is pretty high. So turbulence is of course there, and you are forced to somehow try to solve this issue. So here are the first results. So on the top row, you can find the trend for the eigenvalues for all the variables, so velocity, pressure, energy, and the viscosity. And they are very useful because you somehow have to understand how many basis functions you need for all different for every different variable during the online stage. So we selected 20 model basis functions for all U, P, and E, while 30 model basis functions are used for the head viscosity. While in the middle of the slide, the trends for the loss functions are depicted. So they are two because we divided, let's say, the offline set that we had into two parts, so that one could be used to train the network, and another one could be used to test it and test how it is working. In the sense that when the two trends starts to be far enough one from the other, then you understand that you can just stop your training because your, let's say, neural network is not gonna get better anymore. So So in the bottom row are depicted the errors for all the different values of the parameter. And so as you may see, they are pretty low. So it means that the method is reliable and is working pretty fine. And these are the fields solutions for a random value of the parameter mu. So on the top row are depicted the offline solutions, while in the bottom row are depicted the online solutions for velocity, pressure, and energy. And I mean, if you compare them, they are very similar. That means that, I mean, that the online reconstruction is quite good. While here at the bottom part of the slide is depicted a comparison between the offline solution for NuT and the eddy viscosity reconstructed by the neural network. So also the neural network is doing good. This is the second test case that I wanted to present you. So here, what we are doing is to basically modify the surface of the airfoil by the use of a bump function that is the one depicted here in the top part of the slide. So as you may notice, it is centered on the leading edge of the airfoil. So we are mainly modifying the leading edge of our NACA 0012. So this bump function is added to the top surface and it is subtracted by the bottom surface. And for this reason, we have two different sets of parameters. So these parameters are just the amplitude, let's say, of this bump function. This time we had to also decrease a little bit the inlet velocity because since we are modifying the shape of the airfoil, the velocity is growing in the zones, let's say, of the airfoil where the curvature is high. So since we are modifying its shape, it can happen. I mean, it happened when we tried to keep on working at 250 meters per second, that in some little spots of the domain, the velocity was higher than velocity of sound. But since we are not dealing with shocks in any way, Then, of course, I mean, we had to just decrease a little bit the inlet velocity. So again, we can evaluate the Mach number, that is kind of 0.5, and the Reynolds number, that is something about 10 to the power 7. So, I mean, still compressible, turbulent, Fans equations are required. And these are the same results, but for this new test case. So this time we just selected 30 model basis functions for U, P, and D, and 15 for the eddy viscosity. So here again we have the loss functions, and at the bottom part of the slide you may notice the errors. So again they are pretty low. They are changing more than in the previous case. And it is due to the fact that when you change the geometry the geometry of the problem, then of course the problem is varying much more than in the case of a physical parameterization. So here I just want to show you two different solutions. So in the first one, we are increasing more the curvature of the bottom part of the airfoil, and with respect to the top one, and again you have on the top row the full order solutions, while in the bottom row the reduced order solutions for velocity, pressure, and energy. While in the bottom slide, in the bottom part of the slide, again, you have a comparison between the reconstructed eddy viscosity and with respect to the full one. And while this one, I mean, it is not that easy to be noticed, but they are two different solutions, in the sense that in this second one, we are instead increasing more the top surface of the airfoil with respect to the bottom one. So if we compare them, of course, we can say that the method is pretty reliable. It is, I mean, working as we expected. So, few considerations. So I just try to show you, I mean, an approach for parameterized compressible Navier-Stokes problems, and I tried to convince you that this approach is very usable and versatile, and try to do that by showing you two different test cases, a physical parameterized one and a geometrical test case. But still there are some points that have to be, I mean, optimized. So the neural network can be improved in the sense that, as I showed you, it is a very simple one, and maybe it can be modified to work in an even better way. That's something that we would like to do is to use artificial intelligence also to approximate the online functionals, so that during the online phase, you are not forced to reconstruct the fields anymore, and you can just keep on working with reduced solutions. And last but not least, because of course there's a very important point, some deeper analysis on time consumption have to be taken into consideration. So thank you for your attention. And this was supposed to be me after this talk, but I don't think it's gonna work like that, because as you all maybe know, I'm gonna just keep on writing my PhD thesis. And so, I mean, this is not the case.
Thank you very much, Matteo. Thank you. Thank you for this talk. So now it's question time. if you have a question, you can unmute yourself and ask directly to Matteo.
Okay, I have a question, if I can.
Great.
Of course.
Okay, Matteo, just at the beginning, you told us that basically you are computing some intermediate state for the snapshot. So start from the starting solution to the final solution.
Yeah.
You save some intermediate snapshot.
Yeah, that's right.
And just a curiosity, how many of them in general?
Usually we keep kind of 30 or 40 for every different solution. You have also to think about that you cannot take too many of them, because they are somehow polluting the physical content of your basis functions, because of the fact that, of course, they are not converged solutions, so they are not they don't have a real physical content. So you have to pay attention on how many you put into your set, because otherwise, I mean, you're gonna mess up everything.
Yes, and is there a rule, or it's just problem dependent, I guess?
I think it's really problem dependent. This is just a solution that we tried to, because the online part otherwise was not able to convert.
Okay, thank you.
You're welcome.
Hi, Matteo, it's Gianmarco. I have a question. Hi. When you mentioned that you stop when the training and the testing has, let's say, a gap during the training phase.
Yeah.
Okay, yes, perfectly. That's the right slide. Which is the criterion at termination to measure such a gap? Have you used a sort of fixed fraction?
No, I mean,
stop training?
In my case, I just increase the number of epochs till I see that first the let's say the loss function for the train set is not decreasing anymore that much, and also when the gap between these two is increasing, because you reach at a certain point the two start to diverge a lot. So yes, maybe you keep on performing a bit better on the train set, but the testing set, I mean,
is not improving. Yes, yes.
It's not improving at all.
You also need a sort of stationary situation for the training loss, right? So you have that the training is flat, more or less.
I mean, you're not forced to do that, in the sense that you are just interested to do that, in the sense that yes, when you see that it is not decreasing anymore, you already know that you cannot do any better.
Yes.
While if it is still decreasing, I mean, it is a balance between these two aspects that you have to take into consideration.
That's good. So, but the determination rule is made experimentally, you said, by increasing the number of epochs.
Yeah, in my case,
it's not automatic.
No, in my case, it is like that.
Okay, thank you.
You're welcome.
Okay, there is another question from Andrea. Okay.
Oh, you got me already. So thank you very much, Matteo, for the talk and everything. Can I ask you something? When you described your algorithm in the online phase,
yeah,
it seems to me, I might have got it wrong, so that somehow you get back to the offline mesh during the online phase. Okay, so why is it that you need to do so? Is it because your mesh is moving, or?
I mean, you have to do that because you have to reassemble all the equations at every step. That's basically why we're doing that. So yeah, that is why I told you at the end of the talk that the idea that could be a good idea to use artificial intelligence also to approximate all those functionals.
Okay.
Because yeah, most of all in the geometrical parameterized test cases, you are always forced, I mean, to go back to the mesh. So it is not the best performing that you can.
Yeah, in fact, that's why I thought this happens. I just wanted the confirmation that it was the case.
Yeah.
Okay. It seems to me that there are no more questions, so I thank again Matteo for his talk, and
Thank you.
I thank you all for being with us today, and we see each other next Friday. See you guys.
Bye.